The morning of September 2nd, 1945, Tokyo Bay. Commander Toshikazu Omei stands on the weathered teak deck of the USS Missouri, his dress uniform pressed but somehow feeling inadequate against the grey steel surrounding him. The air smells of salt and oil, and something else, the metallic scent of defeat. His eyes drift past the surrender ceremony preparations, past the gathered American admirals in their crisp whites, past the journalists with their flashbulbs, to the horizon. He begins counting: 1 carrier, 2, 5, 8, 12. 15 fleet carriers visible from where he stands, their grey hulls stretching across Tokyo Bay like a steel curtain. Each one displaces more than 30,000 tons. Each one carries enough aircraft to flatten a city. Each one represents something that his intelligence reports, his calculations, his carefully constructed mathematical models had insisted was impossible. Commander Omei had spent 3 years telling anyone who would listen that the Americans could not build fast fleet carriers at scale, that their shipyards, impressive as they were, could not overcome the fundamental limitations of complexity, skilled labour, and material science. That the Essex-class carrier program announced with such fanfare in 1941 would produce perhaps 4 or 5 ships before industrial bottlenecks strangled the program. He had been catastrophically, unforgivably wrong. The question that haunts him as he watches his superiors prepare to sign away their nation's sovereignty is not how Japan lost the war. That answer is written in the burning ruins of Tokyo, Hiroshima, Nagasaki. The question is simpler and somehow more disturbing. How did the Americans build all these ships? If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. To understand why 24 fleet carriers seemed impossible, you must first understand what Japan knew about building such vessels and what they thought they knew about American capabilities. December 7th, 1941. The attack on Pearl Harbor sends shockwaves through the American Pacific Fleet. 4 battleships sunk outright, 4 more damaged. The Arizona settles to the harbor bottom with over 1,000 men entombed inside her hull. The photographs that reach Tokyo show twisted metal, burning oil, and chaos. The Japanese Naval General Staff celebrates. Admiral Yamamoto, the architect of the attack, does not. In a modest office in the Navy Ministry building in Tokyo, Lieutenant Commander Omei compiles his post-attack assessment. His report is not celebratory. Page after page of careful analysis leads to a conclusion that makes his superiors uncomfortable. The attack on Pearl Harbor, successful as it appears, may have struck the wrong targets. The American battleship fleet is obsolete, he writes. The future of naval warfare belongs to it, the aircraft carrier. Japan has 10 fleet carriers, the United States has 7. But America possesses something Japan cannot match: industrial capacity that operates on a scale Tokyo's planners struggle to comprehend. His report includes calculations, estimates of American steel production, assessments of shipyard capacity, projections of how quickly the United States could replace losses. The mathematics are sound. The conclusion is stark. If this war extends beyond 1 year, American industrial capacity will overwhelm us. They can replace every ship we sink. We cannot replace ours. Admiral Yamamoto reads the report. He has seen American industry firsthand during his years as a naval attaché in Washington and as a student at Harvard. He knows the automobile factories, the steel mills, the vast rail networks. His response to Omei's report becomes one of the war's most haunting prophecies. I shall run wild for the first 6 months or a year, but I have utterly no confidence for the second or third year. The clock begins ticking on December 7th, 1941. Japan has 6 months to win the war before American industry fully mobilizes. 6 months before the sleeping giant awakens. But what neither Yamamoto nor Omei fully grasps in December of 1941 is not just the scale of American production, but the nature of it. They are thinking in terms of how Japan builds carriers. They are about to learn that the United States builds them differently. A fleet carrier in 1941 represents the pinnacle of industrial complexity. Consider the specifications of what would become the Essex-class, 888 feet in length, longer than 3 American football fields laid end to end. 27,000 tons displacement unloaded, swelling to 36,000 tons when fully equipped for combat operations. A crew of 3,448 men, a floating city requiring its own hospital, kitchens, machine shops, and even a post office. Each carrier requires 3 million individual parts fabricated to precise specifications. 22 miles of piping snake through its compartments, carrying steam, water, fuel, and hydraulic fluid. 2,800 separate compartments must be made watertight. The armor belt alone, hardened steel plate, protecting the vital machinery spaces, weighs thousands of tons and must be forged, transported, and installed with millimeter precision. The flight deck presents its own engineering challenges. It must be strong enough to support fully loaded aircraft weighing up to 15 tons, flexible enough to absorb the shock of controlled crashes, and smooth enough to allow safe landings in rough seas. Below the flight deck, the hangar deck must accommodate up to 90 aircraft, with elevators capable of lifting a fully armed dive bomber from hangar to flight deck in under a minute. The propulsion system alone represents a marvel of engineering. 4 steam turbines generating 150,000 shaft horsepower, driving 4 propeller shafts, pushing 36,000 tons of steel through water at speeds exceeding 33 knots. The fuel bunkers must carry enough oil to steam 6,000 miles at cruising speed. For Japan, building such a vessel requires mobilizing every major shipyard in the nation. The carrier Shokaku, completed in 1941, took 30 months from keel laying to commissioning. The even larger Shinano, converted from a battleship hull, would consume 4 years of labor and would sail for barely 10 days before an American submarine sent her to the bottom. In the early 1942, Japanese naval intelligence received reports that the Americans planned to build these ships not 1 or 2, but dozens in less than 2 years per vessel. The Intelligence Bureau analyzes these claims with the same careful methodology Omei had applied to his pre-war assessments. Their conclusion, filed in March of 1942, is unequivocal. The construction of fleet carriers on the scale and timeline reported is technically impossible given known American shipyard capacity, skilled labor requirements, and material constraints. The Americans are likely exaggerating their capabilities for propaganda purposes, or the reported vessels are of inferior quality, unsuitable for front-line operations. The report includes detailed calculations. An Essex-class carrier requires approximately 5 million man-hours of skilled labor. American shipyards employ roughly 200,000 workers with the necessary skills. Assuming optimal efficiency and working exclusively on carrier construction, which would preclude building destroyers, submarines, and other necessary vessels, American yards could theoretically complete 1 carrier every 18 months. But optimal efficiency is impossible. Workers get sick, machinery breaks down, steel deliveries are delayed, and the Americans must build dozens of other ship types simultaneously. Factor in realistic efficiency rates, and the mathematics suggest America might complete 4, perhaps 5 Essex-class carriers during the entire war. The Japanese calculations are thorough. They account for every known variable. They are based on sound engineering principles and accurate intelligence about American shipyard capacity. They are also completely wrong. The mistake lies not in the mathematics, but in the assumptions underlying those calculations. The Japanese analysts are calculating based on how Japan builds ships sequentially, from keel to commissioning, with each step dependent on the completion of the previous step. They assume American shipyards operate on the same principles, merely scaled up. They are about to learn that the Americans have fundamentally reimagined the process of building a warship. April 28, 1941, 7 months before Pearl Harbor. At the Newport News, Shipbuilding and Dry Dock Company in Virginia, workers begin laying the keel of a vessel designated CV-9, the Essex, the lead ship of her class, the first of what will become the Impossible Fleet. The pre-war planning for the Essex-class reveals American strategic thinking that Japan's leaders failed to anticipate. While Japan is preparing for a short, decisive war that will force America to accept Japanese dominance in the Pacific, the United States Navy is designing ships for a long war of industrial attrition. The Essex-class design prioritizes not just combat capability, but producibility. Every decision in the design phase considers how quickly and efficiently the ship can be built. Standardized components, modular construction, prefabrication of entire sections. The Essex-class is designed from the beginning to be mass-produced. Mass production of a 30,000-ton warship. The concept seems absurd, yet even before Pearl Harbor, before America enters the war, the groundwork is being laid for an industrial mobilization unprecedented in human history. June 4th through 7th, 1942. The Battle of Midway. In 4 days of desperate combat, American dive bombers sink 4 Japanese fleet carriers, Akagi, Kaga, Soryu, and Hiryu. Japan's first-line carrier strength is cut in half. These are not just ships. They are the veterans of Pearl Harbor, the Darwin Raid, the Indian Ocean operations. Their loss cannot be easily replaced. Japan's shipyards are already working at capacity. American losses at Midway, 1 fleet carrier, the Yorktown, torpedoed and sank slowly after surviving multiple bomb and torpedo hits. Devastating but replaceable. President Franklin Roosevelt signed the Emergency Shipbuilding Directive on June 25, 1942. The Essex-class program receives Priority 1 status, the highest designation in American war production. Every resource necessary for carrier construction will be made available. Every bottleneck will be broken. Every impediment removed. The directive reaches Newport News in Virginia, the New York Naval Shipyard in Brooklyn, Bethlehem Steel's Fall River Shipyard in Massachusetts, the Philadelphia Naval Shipyard, the Norfolk Naval Shipyard, the Puget Sound Naval Shipyard in Washington State. 7 major shipyards retool their operations for one purpose: build fleet carriers as fast as steel can be cut and welded. But the transformation extends far beyond the shipyards themselves. Across the American industrial landscape, factories begin converting to war production on a scale that staggers comprehension. In Detroit, automobile assembly lines that produced Fords, Chevrolets, and Chryslers shut down civilian production entirely. The factories retool for aircraft engines, tank transmissions, gun mounts. The workers who built family sedans now build weapons of war. General Motors alone will produce war materiel worth $12 billion by 1945, more than the entire economic output of Italy. Steel mills in Pennsylvania, Ohio, Indiana run 24 hours a day. American steel production in 1941, 60 million tons. By 1943, 120 million tons. The increase alone, 60 million tons, exceeds Japan's total steel production capacity. Aluminum production increases even more dramatically. Light metal alloys for aircraft construction become a strategic priority. American aluminum production increases from 300,000 tons in 1941 to 1.8 million tons by 1943. Japan's peak aluminum production, 70,000 tons. The numbers tell a story Japan's planners never fully grasped. America is not trying to balance civilian and military production. The country is converting its entire economy into a war economy. But raw material production, impressive as it is, does not explain how 24 fleet carriers emerge from American shipyards in 40 months. The real revolution occurs in how those materials are transformed into warships. Newport News Shipbuilding, July 1942. The Essex is taking shape in Dry Dock 10, her keel laid, her frame rising. But something is different about how this ship is being built compared to traditional naval construction methods. Traditional Japanese approach to building a warship: construct the hull from keel upward, frame by frame, plate by plate. Install machinery as spaces become accessible. Add weapons systems. Install electronics. Each step follows the previous step in a strict sequence. The process is logical, orderly, and time-consuming. American approach: build the ship in hundreds of separate pieces simultaneously, then assemble them like a three-dimensional puzzle. At factories across Virginia, Pennsylvania, Maryland, enormous sections of the Essex take shape far from the shipyard. Gun mounts weighing 40 tons are assembled, complete wiring, hydraulics, fire control systems, installed then transported by rail to Newport News. Entire compartments, 20 feet by 30 feet by 10 feet, are built as complete units with bulkheads, deck plating, piping, lighting, ventilation ducts all installed. These sections arrive at the shipyard, ready to be lifted by massive cranes and welded into place. The flight deck, traditionally built plate by plate over the hull structure, is instead fabricated in 10 enormous sections. Each section is built on land, flat, with all the arresting gear, catapult tracks, and deck plating installed. Then the sections are lifted onto the hull and welded together. What traditionally took 8 months takes 6 weeks. The electronic suites, radar, radio, navigation equipment are wired and tested in separate workshops, then installed as complete systems. The wiring harnesses alone, which would traditionally require electricians to run thousands of individual wires through the ship's compartments, are instead prefabricated. Entire sections of wiring, already routed and connected, are installed in hours rather than weeks. A worker named Dorothy Cole, employed at Bethlehem Steel's Quincy shipyard in Massachusetts, later recalls, "We'd see these massive pieces arriving by rail from Pennsylvania, from Ohio, from factories we'd never heard of. Complete gun turrets, sections of hull with the compartments already built inside. You could look into them and see bunks, lighting, everything. We just had to lift them into place and weld them in. The Japanese were still hammering out individual hull plates while we were assembling finished sections. The workforce itself represents a revolution. With millions of men in uniform, American shipyards recruit women in unprecedented numbers. Rosie the Riveter is not just propaganda, it is a statistical reality. By 1943, women comprise 40% of shipyard workers. They weld, rivet, operate cranes, read blueprints, inspect welds, and do every job previously considered men's work. Training programs, which traditionally took years to produce skilled shipwrights, are compressed to months or weeks. The modular construction method allows for greater specialization. Workers become experts at one specific task, rather than needing to master all aspects of ship construction. Quality control inspectors ensure that each module meets specifications before installation. The result: construction time drops from 30 months to 20 months, then to 18 months, then to 16 months for later ships in the class. The Americans are not just building faster, they are learning how to build faster with each ship completed. Commander Omei receives the intelligence report in December of 1942. USS Essex, hull number CV-9, has been commissioned into the United States Navy. Construction time from keel to commissioning, 20 months. He studies the report carefully. The Essex displaces 36,000 tons fully loaded. She carries 90 aircraft. Her specifications match or exceed Japanese fleet carriers. This is not an inferior vessel rushed into service. This is a frontline warship of the highest quality. Omei's analysis: the Essex represents a one-time achievement. The Americans have concentrated their resources to produce a single ship quickly for propaganda purposes. They cannot maintain this pace. The complexity of fleet carrier construction, the skilled labor requirements, the demands on steel production, all ensure that future carriers will take longer to build as resources are stretched across multiple projects. His report to the Naval General Staff includes detailed calculations showing why sustained production is impossible. American steel output, even at increased production levels, cannot support building multiple fleet carriers simultaneously while also producing the destroyers, submarines, cruisers, and merchant vessels necessary for global operations. Material bottlenecks will slow production. Skilled labor shortages will develop. The Americans will need to choose which ship types to prioritize. The report concludes: expect 3 to 4 additional Essex-class carriers by late 1943, with diminishing production thereafter as industrial constraints become binding. His mathematics is impeccable. His logic is sound. His understanding of industrial production is sophisticated and thorough, and he is wrong. Completely, utterly, catastrophically wrong. Because something is happening in America that has never happened before in human history. An entire continental economy is converting itself into a machine for producing war materiel, not partially, not gradually, totally and immediately. Civilian automobile production in America, 0 vehicles in 1943. Every automotive factory is building military equipment. Civilian radio production, halted. The factories build military radios. Civilian aircraft production, non-existent. Every aircraft factory builds warplanes. Refrigerator factories build ammunition. Typewriter companies manufacture gun components. Toy manufacturers stamp out compass casings. Rationing extends to virtually everything. Gasoline, meat, sugar, coffee, shoes, tires. Civilians make do with less, so that soldiers, sailors, and war workers can have more. The American gross domestic product increases by 70% between 1941 and 1944. Virtually all that increase goes to military production, and the workforce expands in ways Omei's calculations never accounted for. Women enter factories. African Americans migrate from the segregated South to industrial centers in the North and West, finding employment in war plants that previously excluded them. Older workers return from retirement. Teenagers work after school. The American industrial workforce grows from 46 million to 54 million between 1941 and 1943. The shipyards operate in 3 shifts, 24 hours per day. Arc welders create constellations of sparks in the darkness. Cranes swing enormous steel sections through the night. The hammering never stops. In dry docks along both coasts and the Gulf of Mexico, fleet carriers take shape with assembly line efficiency. January 21, 1943. USS Yorktown, hull number CV-10, second of the Essex-class, is commissioned. Construction time, 19 months. April 15, 1943. USS Intrepid, CV-11. Construction time, 18 months. August 17, 1943. USS Hornet, CV-12. Construction time, 17 months. The ships keep coming, not 3 or 4 as O'May predicted, not slowing as industrial constraints bite, accelerating. Each shipyard learns from the previous ship, refining procedures, eliminating inefficiencies. What seemed impossible becomes routine. By the end of 1943, 9 Essex-class carriers had been commissioned, 9 30,000-ton fleet carriers in 24 months. Japan's total carrier construction during the same period, 2 escort carriers. The statistical disparity becomes so extreme it verges on the absurd. But these are not statistics. These are ships. Real vessels with steel hulls and wooden decks, carrying real aircraft flown by real pilots, protected by real anti-aircraft guns manned by real crews. And they are coming across the Pacific in numbers that Japan cannot counter, cannot sink faster than they are built, cannot match with any industrial effort Japan can mount. Commander O'May tracks each new commissioning with growing horror. His reports to the Naval General Staff became increasingly dire. By mid-1943, the Americans have exceeded predicted production capacity. Recommend immediate escalation of carrier construction. By late 1943, American carrier production continues at an unsustainable pace. We must assume they are accepting inferior quality to maintain numbers. By early 1944, silence. The reports stop. The numbers speak for themselves. Japan's total carrier construction program from 1942 through 1945 produces 6 fleet carriers. The United States, during the same period, commissions 24 Essex-class carriers alone, plus 9 Independence-class light carriers converted from cruiser hulls, plus over 100 escort carriers built on merchant ship designs. But raw numbers, staggering as they are, do not fully capture the nature of American industrial dominance. Because the Essex-class carriers are not just numerous, they are better than what came before. The design incorporates lessons learned from earlier American carriers and from studying Japanese carrier operations. The result is a vessel more survivable, more capable, and more adaptable than any carrier previously built. Damage control represents perhaps the most critical improvement. Earlier, American carriers like the Lexington and Yorktown proved vulnerable to cascading damage. A single torpedo or bomb hit could trigger fires that spread uncontrollably, secondary explosions that gutted the ship, flooding that could not be contained. The Essex-class design addresses these vulnerabilities systematically. The hull is divided into hundreds of watertight compartments. Damage to one section can be isolated, preventing flooding from spreading. Multiple redundant systems ensure that if one pump fails, others can take over. If one generator is destroyed, others continue providing power. The aviation fuel system incorporates a revolutionary safety feature. Fuel lines can be filled with inert carbon dioxide gas, preventing fuel vapors from igniting even if the lines are ruptured. Earlier carriers had burned because aviation fuel vapor, more explosive than the fuel itself, ignited from any spark. Fire suppression systems are distributed throughout the ship. Foam generators can blanket hangar decks in fire-retardant foam within minutes. Sprinkler systems activate automatically. Firefighting parties are trained to a level of proficiency that transforms damage control from desperate improvisation to systematic procedure. The armor scheme protects vital spaces without adding excessive weight. The machinery spaces, magazines, and aviation fuel tanks are surrounded by multiple layers of protection. The flight deck itself, while not armored like a British carrier, is designed to be rapidly repaired, even if heavily damaged. These design features are not theoretical. They will be tested in combat under the most severe conditions imaginable. March 19, 1945. USS Franklin, CV-13, operating off the coast of Japan as part of Task Force 58. The carrier has just completed arming and fueling 51 aircraft on her hangar deck for a strike mission against Japanese airfields on Kyushu. Fully armed and fueled aircraft represent the most dangerous possible moment bombs, rockets, torpedoes, and full fuel tanks, all concentrated in an enclosed space. At 7:08 in the morning, a single Japanese dive bomber penetrates the American Combat Air Patrol. The pilot releases two 500-pound bombs from low altitude. Both bombs hit Franklin. Both penetrate the wooden flight deck. Both detonate inside the hangar deck where the armed and fueled aircraft wait. The result is catastrophic. Bombs detonate, rockets ignite and tear through bulkheads. Torpedoes explode. Aviation fuel ignites, creating a firestorm. The Franklin's hangar deck becomes an inferno. Explosions rip through the ship. Men are incinerated instantly. Others are blown overboard. The carrier lists 13 degrees to starboard as firefighting water accumulates on one side. 724 men die in the first hour, the worst casualties ever suffered by a United States warship that survived the attack. Japanese intelligence, monitoring American radio, the traffic, reports that a fleet carrier has been mortally wounded. Post-war analysis will surely show she sank. No carrier could survive such damage. USS Franklin does not sink. The crew fights the fires for 5 hours before bringing them under control. The engineering department restarts the engines. Franklin makes way under her own power, achieving 14 knots despite massive damage. She sails 12,000 miles to the Brooklyn Navy Yard, arriving on April 28th. Repairs take 8 months. She returns to service. The Franklin survives because every damage control feature designed into the Essex-class works as intended. Watertight doors contain flooding. Redundant systems provide power and pumping capacity even as entire sections are destroyed. The crew, trained to the highest standard, performs with extraordinary courage and discipline, and the ship herself, built with structural strength that seems excessive in peacetime, proves barely adequate for wartime survival. Compare this to Japanese carrier survivability. June 19th, 1944, the Battle of the Philippine Sea. The carrier Taiho, Japan's newest and most advanced fleet carrier, is struck by a single torpedo from the American submarine USS Albacore. The torpedo damages the hull, but does not immediately threaten the ship. However, aviation fuel lines rupture. Fuel vapors accumulate in the hangar deck and lower compartments. An inexperienced damage control officer orders ventilation fans turned on, hoping to clear the fumes. Instead, the fans distribute fuel vapor throughout the ship. 7 hours after the torpedo hit, the vapor ignited. The explosion guts the Taiho. She sinks within hours. Over 1,600 men die. A single torpedo, poor damage control, inadequate design. The newest Japanese carrier is destroyed by damage. An Essex-class carrier would survive. This pattern repeats throughout the war. American carriers prove extraordinarily difficult to sink. USS Yorktown at Midway survives multiple bomb and torpedo hits, remaining afloat for 2 days before finally succumbing to submarine torpedoes. USS Hornet at Santa Cruz absorbs multiple bomb hits, kamikaze crashes, and torpedo hits before finally sinking, and even then, requires American destroyers to finish her off when she refuses to go down. Japanese carriers, despite their excellence in other areas, prove fragile. Wooden flight decks burn. Inadequate fire suppression allows small fires to become uncontrollable. Aviation fuel systems lack safety features. Damage control training is insufficient. The industrial capacity to build many carriers combines with design excellence to create resilience. America can afford to take risks because losses can be replaced. Japan cannot afford to lose any carrier, yet loses them more easily when hit. But ships alone do not fight wars. Each Essex-class carrier requires 90 to 100 aircraft. Each aircraft requires a pilot. And here, the disparity between American and Japanese capability becomes even more stark than in shipbuilding. Japan begins the war with the finest carrier pilots in the world. The pilots who attack Pearl Harbor, who dominate the early campaigns in the Pacific, average over 5,000 hours of flight time. They are superbly trained, experienced, and tactically skilled. They fly the Zero, an aircraft that can outmaneuver anything the Allies possess in 1941. But these pilots are irreplaceable. Japanese pilot training, which takes 24 months to produce a carrier-qualified aviator, cannot keep pace with combat losses. And the losses, from the beginning, are severe. At the Battle of the Coral Sea in May 1942, Japan lost 69 aircraft and their crews. At Midway in June, over 100 aircraft and pilots were lost when the 4 carriers sank. These losses represent not just machines, but highly trained specialists who cannot be quickly replaced. The Imperial Japanese Navy's training infrastructure cannot expand rapidly. Training carriers are in short supply. Fuel for training flights becomes scarce as Japan's oil situation deteriorates. Experienced instructors are pulled from training duties to fly combat missions. The training pipeline, already slow, becomes slower. By 1943, Japanese pilot training time dropped from 24 months to 18 months, then to 12 months, then to 6 months. By 1944, some pilots receive as little as 3 months of training before being assigned to frontline units. And for kamikaze pilots, those designated for suicide missions training is reduced to the absolute minimum required to take off and navigate to a target. They do not need to learn how to land. American pilot training, by contrast, expands and improves throughout the war. In 1941, carrier pilot training takes approximately 12 months. By 1943, training time increases to 30 months, not because American pilots are slower learners, but because the training has become more comprehensive and sophisticated. American pilot trainees fly more hours before earning their wings than Japanese pilots flew in their entire training program. They train on multiple aircraft types. They practice gunnery until hitting targets becomes instinctive. They drill formation, flying, navigation, carrier landings, and combat tactics until these skills are automatic. And unlike Japan, America has no shortage of training resources. Fuel is abundant. Aircraft are abundant. Thousands of training aircraft roll off production lines, separate from combat aircraft production. Airfields are abundant. Instructors are abundant. Experienced combat pilots rotate home to train the next generation, passing on lessons learned over Japan and the Pacific Islands. The result: by 1944, the average American carrier pilot is better trained, more experienced, and flying superior aircraft than his Japanese opponent. The qualitative gap that favored Japan in 1941 has reversed completely. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Lieutenant Commander Alexander Vrasiu, a carrier pilot flying from USS Lexington, later recalled an engagement in June of 1944 during the Battle of the Philippine Sea. I could see them coming in Japanese planes in formation, but the formation was ragged, not tight like the formations we'd seen in 42, and the way they maneuvered when we engaged them. These weren't the guys who hit Pearl Harbor. These were kids. Brave kids, doing their best, but you could tell they hadn't had enough training. It was like watching someone who'd learned to drive last week trying to race against professionals. Vrasiu shot down 6 Japanese aircraft in 8 minutes during that engagement. He was not unique. Many American pilots achieved ace status, 5 or more aerial victories within months of reaching the combat zone. Japanese aces, those few who survived long enough to achieve such status, were vanishingly rare by 1944. The Americans were not building just carriers. They were building an entire system. Carriers, aircraft, pilots, mechanics, fuel, ordnance, spare parts, all flowing from an industrial and training base that Japan could not match or attack. Consider the logistics. Each Essex-class carrier burns 400 tons of fuel oil per day at cruising speed, more at flank speed. Each carries 90 aircraft that collectively consume thousands of gallons of aviation fuel daily during operations. Ammunition expenditure during a single day of intense combat operations can run to hundreds of tons. Anti-aircraft shells, bombs, torpedoes, bullets. Traditional naval operations required carriers to return to port regularly to refuel, rearm, and replenish supplies. This limited their operational range and flexibility. The Americans solved this problem with a logistics innovation as revolutionary as the carriers themselves. Underway replenishment, fleet oilers, ammunition ships, and supply vessels accompany the carrier task forces. At sea, in the open ocean, these support ships come alongside the carriers. Hoses are connected, fuel flows, pallets of ammunition and supplies are transferred via cable. The carrier never stops moving. The operation takes hours rather than the days required for a port visit. This capability extends the American carrier's striking range indefinitely. Task Force 58, the Fast Carrier Task Force, operates continuously for months without returning to port. Carriers steam from the Central Pacific to the Philippines, to Okinawa, to Japan itself, refueling and rearming at sea. Japanese bases cannot be safe because American carriers can strike anywhere, anytime, and sustain operations indefinitely. Japan lacks this capability. Japanese carriers must return to port to refuel and rearm. This limits their operational flexibility and makes them vulnerable during transit to and from bases. Japanese supply ships are also vulnerable to American submarines, which wage unrestricted warfare against Japanese merchant shipping. By 1944, moving supplies by sea within Japanese-controlled waters became increasingly dangerous. The submarine campaign represents another dimension of American industrial superiority. The United States Navy commissioned 203 submarines during the war. These submarines sink over 50% of Japanese merchant shipping, nearly 5 million tons. They also sank 1 battleship, 8 carriers, and 11 cruisers of the Imperial Japanese Navy. Japan commissioned 130 submarines during the same period. Japanese submarines sink few merchant ships. Their primary mission is attacking warships and achieve limited success against American naval forces. American anti-submarine warfare, employing destroyer escorts built in the hundreds, proves devastatingly effective. By late 1944, the cumulative effect of American industrial production became overwhelming. Japan's navy, which began the war as one of the most powerful in the world, is reduced to a hollow shell. Fuel shortages mean ships cannot sail for training or operations. Pilot losses mean carrier decks sit nearly empty. Production bottlenecks mean new ships commission without adequate fire control systems or radar. Entire fleet units become immobile, conserving fuel, waiting for a final battle that never comes on terms favorable to Japan. The Battle of Leyte Gulf in October 1944 represents Japan's last attempt to employ its carrier force effectively. 4 carriers, Zuikaku, Zuiho, Chitose, and Chiyoda, are assigned as decoys to lure American carriers away from the landing beaches at Leyte. The plan requires the Japanese carriers to be so obviously threatening that the Americans must pursue them. The Japanese carriers carry approximately 100 aircraft total between all 4 ships. They are not threatening, they are bait. And they succeed in their mission. American carriers pursue them northward, but the cost is absolute. All 4 Japanese carriers are sunk. Japan's carrier force ceases to exist as an effective fighting force. The Americans at Leyte Gulf deploy 16 fleet carriers, 16 Essex-class and light carriers, carrying over 1,000 aircraft, supported by dozens of escort carriers operating hundreds more planes. The numerical disparity is so overwhelming that individual American carrier groups possess more striking power than the entire Japanese carrier force. Commander Omei, reading the battle reports in Tokyo, drafts a memo that will never be officially filed. He writes, "We are not fighting a nation. We are fighting an industrial system that treats 30,000-ton warships as mass-produced articles of commerce, building them with the efficiency that we might build trucks. We calculated their shipyard capacity correctly. We measured their steel production accurately. We assessed their skilled labor force thoroughly. All our intelligence was correct. What we failed to understand was that they would rebuild their entire economy around warship production, that they would train new workers in months to do jobs that require years to learn, that they would invent new methods of construction that violate traditional shipbuilding practice but somehow work. We were not wrong about what was possible. We were wrong about what the Americans would consider acceptable." The memo remains in Omei's papers, unsubmitted. There is no point. The war is already lost. The only question remaining is how long until Japan accepts the inevitable. By spring of 1945, American carrier task forces operated in Japanese home waters with impunity. They strike Tokyo. They strike Kobe, Osaka, and Nagoya. They bombard coastal targets with naval gunfire. They sweep the seas of remaining Japanese shipping. They control the air, the surface, and the undersea environment completely. The kamikaze attacks, Japan's last desperate tactical innovation, inflict casualties and damage but cannot alter the strategic situation. Kamikaze pilots dive their bomb-laden aircraft into American ships, achieving hits through suicidal determination that conventional attacks cannot match. They damage dozens of ships. they sink several, but they cannot sink enough. For every ship damaged, replacements arrive from American shipyards. For every sailor killed, trained replacements come forward. The mathematics of attrition favor the side that can replace losses indefinitely. USS Bunker Hill, CV-17, is hit by 2 kamikaze aircraft on May 11, 1945. Fires rage. Nearly 400 men die. The carrier is knocked out of the war, but 15 other Essex-class carriers remain operational. The task force continues operations without pause. By August of 1945, the American Pacific Fleet included 19 Essex-class carriers in frontline service. 5 more are completing workups or repairs. The United States Navy possesses more carrier striking power concentrated in the Pacific than the combined carrier forces of all nations in 1941. Japan has no carriers operational. 0. The last Japanese carrier, Hosho, a small, obsolete vessel from the 1920s, sits in port, disarmed, used for transport. The Naval General Staff cannot even contemplate carrier operations. There are no pilots trained in carrier operations. There is no fuel to conduct training. There is no point. August 6, 1945. The atomic bomb destroys Hiroshima. August 9th. The second bomb destroys Nagasaki. August 15th. Emperor Hirohito addresses the Japanese nation by radio, announcing surrender. The war is over. The surrender ceremony is scheduled for September 2nd aboard the USS Missouri in Tokyo Bay. Admiral Nimitz, commanding the Pacific Fleet, orders a display of force, a demonstration of the industrial might that defeated Japan. Every available carrier is ordered to Tokyo Bay. September 2nd, 1945. Commander Toshikazu Omei boards the USS Missouri for the surrender ceremony. As his motor launch approaches the battleship, he sees the carriers: Essex, Yorktown, Intrepid, Hornet, Franklin, Ticonderoga, Randolph, Lexington, Bunker Hill, Wasp, Hancock, Bennington, Boxer, Bonhomme, Richard, Antietam, 15 Essex-class carriers, plus the light carriers, plus the escort carriers providing air patrol. The horizon is filled with grey hulls. Each one represents something his intelligence assessments declared impossible. Each one carries the name of a lost American ship or a Revolutionary War battle, names chosen to symbolize American resilience and historical memory. Each one floats as evidence of industrial capacity beyond Japan's ability to match or even comprehend. A Japanese naval officer standing near Omei whispers, "How did they build so many?" Omei has spent 4 years attempting to answer that question. His reports fill filing cabinets in the Navy Ministry. His calculations, his projections, his intelligence assessments all wrong, all based on correct data and sound reasoning that nonetheless failed to predict reality. They decided to. Omei finally responds. It is not a satisfactory answer. It is the only answer. The surrender ceremony proceeds. General MacArthur accepts the Japanese surrender. Admiral Nimitz signs for the United States. Foreign Minister Shigemitsu signs for Japan, his hand shaking slightly as he affixes his signature to the instrument of surrender. The war is over. Omei departs the Missouri, returning to Japanese custody, to occupation, to a defeated nation. Behind him, the impossible fleet sits at anchor. 24 Essex-class fleet carriers completed. 9 more under construction. Never finished because the war ended before they were needed. 33 carriers total planned, built, or partially built in 52 months. Japan built 6 carriers in the same period. The ratio, 5.5 to 1. but the ratio understates the disparity because Japanese carriers were smaller, carried fewer aircraft, and were less survivable. In terms of effective combat power, the ratio approaches 10-1 or higher. After the war, American naval intelligence conducted extensive interviews with surviving Japanese naval officers. The interviews seek to understand Japanese decision-making, strategic planning, and intelligence assessments. When asked about the Essex-class program, Admiral Koshiro Oikawa, who served as Navy Minister, provides testimony that enters the historical record. "We calculated that America would need to choose priorities: build carriers, or build tanks and aircraft for Europe, or build merchant ships for supplying Britain and later for invasion operations. We believed they could not do all three at maximum capacity simultaneously. Our calculations showed that doing all three was unprecedented. We were correct that it was unprecedented. We were incorrect that unprecedented meant impossible. They chose not to choose. They did everything." The statistical record supports Oikawa's admission. American war production from 1942 through 1945. 24 Essex-class fleet carriers, 9 Independence-class light carriers, over 100 escort carriers, 349 destroyers, 203 submarines, 952 other major combatants including cruisers, destroyer escorts, and amphibious vessels. Simultaneously, 88,000 tanks, 324,000 aircraft, 64,000 landing craft, 5,777 merchant ships totaling over 38 million tons, total tonnage of naval and merchant shipping over 53 million tons. Japanese production in the same period, approximately 1.8 million tons of naval and merchant shipping combined. The ratio, nearly 30-1. These numbers are not projections or estimates. They are historical facts, documented in production records, commissioning ceremonies, and ship registries. Every vessel listed was built, launched, commissioned, and served. Most survived the war. Many served for decades afterward. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now. And don't forget to subscribe. The morning air in Tunisia carried the scent of cordite and sun-baked sand. It was May 19, 1942, and Corporal James Mitchell of the 1st Infantry Division crouched behind a low stone wall near Gazala, his hands gripping his M1 Garand so tightly his knuckles had gone white. He had been in North Africa for 6 weeks, long enough to know the difference between Italian machine gun fire and German, long enough to understand that the steady chatter of an MG-34 meant you kept your head down and waited for your squad's Browning to answer back. But the sound that split the air that morning was something entirely new. It didn't sound like gunfire at all. It sounded like fabric being torn apart, like a giant zipper being pulled at impossible speed, like a carpenter's saw biting through hardwood. 25 rounds per second. His brain couldn't distinguish individual shots anymore. They had blurred into one continuous, mechanical scream that seemed to vibrate in his chest cavity. This was his first encounter with the MG-42, and in the space of 10 seconds, everything he thought he knew about German engineering was about to be proven catastrophically wrong. The weapon that would come to be known as Hitler's buzzsaw had arrived on the battlefield, and American soldiers were wholly unprepared for what it represented. Within weeks, captured examples would be sent back to ordnance depots for examination. Within months, those same weapons would become objects of both derision and dread. And within 2 years, American engineers would attempt and fail spectacularly to copy what they had initially dismissed as crude German desperation. This is the story of how a machine gun made from stamped metal sheets changed American perceptions of enemy capability, reshaped infantry tactics across all theaters of war, and created a legend that would outlive the conflict itself by 7 decades. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. To understand why American soldiers reacted the way they did when they first captured an intact MG-42 in the summer of 1942, you must understand what they had been taught to believe about American industrial superiority. The United States Army of 1942 was an institution built on certain fundamental assumptions about manufacturing quality and engineering excellence. American weapons were precision instruments, each component machined from solid steel blocks using techniques that required skilled labor and considerable time. The M1 Garand rifle, for instance, represented the pinnacle of this philosophy, a semi-automatic rifle with a gas-operated mechanism so finely crafted that each weapon required extensive hand-fitting of parts during assembly. The Browning automatic rifle, the squad-level light machine gun that American infantry relied upon, featured beautifully milled components and tolerances measured in thousandths of an inch. Even the standard-issue M1919 Browning machine gun, the belt-fed weapon that provided covering fire for advancing infantry, was a masterpiece of traditional gunsmithing, heavy, yes, but built to exacting specifications with parts that would last for decades of hard use. This manufacturing philosophy reflected broader American assumptions about the relationship between quality and appearance. A well-made weapon should look well-made. It should have the heft of solid metal, the smooth surfaces of careful machining, the tight tolerances that spoke of precision craftsmanship. These were not merely aesthetic preferences, they were deeply embedded principles of American industrial culture, born from decades of manufacturing experience and reinforced by the very real success of American arms in the Great War. When American doughboys had gone to France in 1917 and 1918, they had brought weapons that worked, that could be maintained in the field, that represented the best traditions of American manufacturing. The Browning M1917 machine gun, water-cooled and heavy as a small anvil, had proven itself in the trenches of the Western Front. It fired the .30-06 Springfield cartridge with methodical reliability, roughly 500 rounds per minute, steady as a metronome. It could fire for hours without failure if properly maintained. It was, by every measure that mattered to American ordnance officers, a superior weapon. This same confidence extended to American assessments of enemy capabilities. German weapons captured during the First World War had been examined and found to be well made, certainly, but not superior to American equivalents. The German Maxim guns were effective but required extensive manufacturing time and resources. Their rifles were bolt-action designs that, while accurate, were slower to operate than the semi-automatic weapons American industry was developing. By 1942, when the United States entered World War II as a full combatant, American ordnance experts believed they understood the trajectory of weapons development. The future belonged to precision manufacturing, to weapons that combined firepower with reliability through careful engineering and quality materials. The German military, they assumed, would continue to produce weapons in this same tradition, perhaps even more elaborately, given German tendencies toward over-engineering. The MG-34, the standard German machine gun at the war's outset, seemed to confirm these assumptions perfectly. When American intelligence officers examined captured MG-34s in North Africa, they found exactly what they expected: a superbly crafted weapon with machined components, careful tolerances, and a design philosophy that emphasized versatility and precision. The MG-34 could function as a light machine gun on a bipod, a medium machine gun on a tripod, or even be mounted in vehicles and aircraft. It featured a clever quick-change barrel system, a dual-feed mechanism that could accept either belt-fed ammunition or a drum magazine, and a rate of fire around 850 rounds per minute, substantially faster than the American Browning, but still within the range that American tactical doctrine could comprehend and counter. The MG-34 was, American analysts concluded, an excellent weapon, but it was also expensive and time-consuming to produce, requiring roughly 150 man-hours of skilled labor to manufacture a single gun. This fit perfectly with American assumptions about German military production. The Germans made good weapons, but they required extensive resources and manufacturing time. In a war of industrial attrition, American mass production would inevitably overwhelm German quality. Then came the summer of 1942, and with it, the first encounters with something entirely different. The German Afrika Korps, locked in a desperate struggle with British Commonwealth forces across the deserts of North Africa, had received new weapons. In May of that year, at places like Gazala and Bir Hakeim, Allied soldiers began reporting a new German machine gun with a distinctly different sound. It wasn't the steady chatter of the MG-34. It was faster, more continuous, almost insect-like in its mechanical fury. British soldiers, veterans of 2 years of desert warfare, described it as sounding like tearing cloth. Commonwealth troops from various nations developed their own descriptions. The Australians called it Spandau, mistakenly believing the name stamped on captured weapons referred to the manufacturer rather than a Berlin district where some were produced. By late summer, as American forces joined the North African campaign in earnest, they too began encountering this new weapon, and captured examples started making their way back to Allied ordnance depots for examination. What American ordnance officers found when they first examined a captured MG-42 in the autumn of 1942 must have seemed almost incomprehensible. The weapon was made from stamped metal, not machined from solid steel blocks, but pressed and formed from sheet metal, like a tin can or a filing cabinet. The receiver, the barrel jacket, the feed mechanism cover all stamped components, spot-welded and riveted together. The surface finish was rough compared to American weapons. You could see the seams where pieces had been joined. The tolerances were looser, the fit less precise. To eyes trained in traditional gunsmithing, trained to associate quality with elaborate machining and tight tolerances, the MG-42 looked crude. It looked cheap. It looked like something assembled hastily from whatever materials were available. One ordnance report from this period, written by an American captain, examining a captured specimen, noted with evident disdain that the extensive use of stamping, riveting, and spot welding gives the gun a less finished appearance than that of the MG-34. The implication was clear. This was a weapon born of German desperation, a corner-cutting response to material shortages and production bottlenecks. This initial assessment spread rapidly through American military circles. Soldiers in the field, shown captured MG-42s by intelligence officers, reportedly laughed at the crude construction. "Look at this garbage," one sergeant was said to have remarked, though the exact quote cannot be verified from primary sources. "Jerry's so desperate he's making guns out of scrap metal now." The sentiment, if not the precise words, was widely shared. American GIs had been raised on stories of German over-engineering, of Tiger tanks with complex transmissions, and Messerschmitt fighters with intricate fuel systems. Here, finally, was evidence that the German war machine was beginning to crack under pressure. They were abandoning quality for quantity, precision for expedience. It confirmed what every American wanted to believe in 1942, that the tide was turning, that German industrial capacity was faltering, that the weight of Allied production would inevitably crush the Wehrmacht's ability to equip its forces with effective weapons. This comforting assessment lasted approximately 6 weeks. By February of 1943, the laughter had stopped entirely. American ordnance authorities had conducted extensive testing on captured MG-42s, firing thousands of rounds under controlled conditions, measuring performance characteristics, analyzing failure modes, and comparing capabilities to American equivalents. The report they published in February 1943 was remarkable not for what it said about German weaknesses, but for what it revealed about American misconceptions. The MG-42, despite its crude appearance, was functionally superior to every machine gun the Allies possessed in nearly every measurable category. Its rate of fire averaged 1,200 rounds per minute, more than double that of the American Browning, more than twice the British Bren gun's output, even substantially faster than its predecessor, the MG-34. But the numbers alone didn't capture what this meant in practical terms. When you fire a machine gun at 1,200 rounds per minute, something psychologically significant happens. The human ear can distinguish individual sounds up to roughly 10 to 15 discrete events per second. Beyond that threshold, separate sounds begin to blur together into a continuous tone. The MG-42 fired 20 rounds per second. Your brain simply could not process it as individual shots. Instead, you heard one long, continuous noise, that distinctive tearing sound, that buzzsaw roar that would become the weapon's defining characteristic. For soldiers on the receiving end, this created an effect unlike any other weapon on the battlefield. You couldn't count the rounds. You couldn't estimate the firing pattern. You couldn't use auditory cues to judge when the gunner might need to reload or when a burst would end. It was continuous mechanical violence, and it shaped everything about how infantry approached German positions. Moreover, the testing at Aberdeen Proving Ground and other American ordnance facilities revealed that the crude construction actually provided unexpected advantages. The loose tolerances that looked like poor craftsmanship. They meant the weapon could function reliably in conditions that would jam more precisely made guns. Sand, mud, extreme cold, extreme heat, the MG-42 kept firing. The stamped metal construction that seemed cheap, it meant the weapon could be produced in 75 man-hours instead of the MG-34's 150 hours, a 50% reduction in manufacturing time. It required only 27.5 kilograms of raw materials instead of 49 kilograms, a 44% reduction. And it cost 250 Reichsmarks to produce instead of 327, a 24% cost reduction. The Germans hadn't abandoned quality for quantity. They had achieved both simultaneously through manufacturing innovations that American industry had never seriously considered for military weapons. The quick-change barrel system was particularly impressive to American ordnance officers. A trained German soldier could swap out an overheated barrel in less than 10 seconds without tools. The barrel simply hinged out to the side, the hot barrel was removed with an asbestos mitt, a fresh barrel was inserted, the mechanism was closed, and the gun was ready to fire again. This meant that the MG-42's theoretical rate of fire could be sustained far longer than comparable weapons. American doctrine recommended changing machine gun barrels after firing roughly 250 rounds in sustained fire to prevent dangerous overheating. The Germans had designed their weapon around this reality, making barrel changes so fast and simple that it barely interrupted the weapon's output. German machine gun teams typically carried 6 spare barrels, rotating them continuously during extended engagements. The pile of hot barrels beside an MG-42 position became a visual signature of German defensive positions across every theatre of war. But perhaps most disturbing to American tactical thinkers was what the MG-42 revealed about German infantry doctrine. American and British military theory in 1943 emphasized the rifleman as the primary infantry weapon. Machine guns provided supporting fire, covering fire to allow rifle squads to maneuver, suppressive fire to keep enemy heads down while riflemen advanced. The machine gun was a support weapon, important certainly, but secondary too. The rifles that actually decided infantry engagements. German doctrine, particularly as it evolved after the introduction of the MG-42, was precisely the opposite. In German infantry squads, the machine gun was the primary weapon. Everything else existed to support it. The rifleman's job was to carry extra ammunition for the machine gun, to protect the machine gun crew, to maneuver so that the machine gun had clear fields of fire. This wasn't merely theoretical. Captured German training manuals made it explicit, and battlefield observations confirmed it. German infantry squads maneuvered around their machine gun positions. On defense, they sighted their positions to provide interlocking fields of fire for their MG-42s. On offense, they used the overwhelming suppressive fire of the MG-42 to pin down defenders, while small assault groups maneuvered to close range. This tactical reality, combined with the weapon's technical capabilities, created severe problems for Allied infantry. Consider the experience of a typical American rifle squad approaching a German defensive position in Italy or France in 1943 or 1944. The squad might consist of 12 men, a squad leader, usually a sergeant, and 11 riflemen, some equipped with M1 Garands, some with Browning automatic rifles for additional firepower. Their job was to close with and destroy the enemy, to seize and hold ground, to accomplish the fundamental task of infantry warfare. To do this, they had to move across open ground, from cover to cover, suppressing enemy positions with their own fire, while maneuvering to advantageous positions. This was difficult enough against any machine gun. Against an MG-42, it became exponentially more dangerous. The sound alone created psychological effects that American training had not prepared soldiers to handle. When that distinctive tearing roar erupted from a concealed German position, even veteran soldiers experienced a moment of instinctive terror. Your subconscious mind, even if your conscious thoughts knew better, interpreted that sound as representing more danger than it could rationally quantify. You knew, intellectually, that each individual bullet was no more dangerous than a single round from any other weapon. But your nervous system, your limbic system, your most basic survival instincts, heard that continuous roar and screamed warnings that bypassed rational thought. Green replacements, new soldiers experiencing their first combat, sometimes froze entirely when they heard an MG-42 open fire. They would drop flat and refuse to move, paralyzed not by cowardice but by sensory overload, by a sound their brains interpreted as representing impossible levels of threat. Even experienced soldiers found the MG-42 psychologically taxing in ways that other weapons were not. A veteran infantry sergeant, interviewed in Sicily in 1943, described the experience this way: "It's the speed that gets you. With our Brownings, you can count the shots, you can feel the rhythm. You know when a burst is ending, when they might be reloading. With the German gun, there's no rhythm. It's just continuous. You can't count it, can't predict it. You just know there's more lead in the air than you can possibly dodge, and you better find good cover fast. This psychological component became so significant that the United States War Department took the extraordinary step of producing a training film specifically designed to reduce soldiers' fear of the MG-42. War Department Film Bulletin No. 181, Automatic Weapons, American versus German, was released in 1944, intended for screening to troops preparing for deployment to the European theatre. The film is fascinating less for what it says than for what its very existence reveals about the severity of the problem. The narrator's tone throughout is determinedly reassuring, almost condescendingly so. Their bark is worse than their bite, he intones at one point, as if the distinctive sound of an MG-42 were merely an audio curiosity rather than the audible signature of devastating firepower. The film shows a dramatized scene, a young replacement soldier experiencing his first combat action, participating in an attack on a German position defended by an MG-42. The replacement is visibly frightened when he hears the weapon's characteristic roar. The narrator comments, "Listen to that, fast. That thing sprays a lot of lead." And you're scared because the German gun fires faster than anything you've run into before, so much faster than the slow, steady bark of American machine guns you heard all through training. But then comes the film's reassurance, delivered with the absolute confidence of official propaganda. Well, so it does have a high rate of fire. Does that mean it is a better fighting weapon than ours? The film then proceeds to a carefully staged comparison. American machine gunners and German gunners using captured MG-42's fire at identical targets. The demonstration attempts to show that American guns, firing more slowly but supposedly more accurately, put more rounds on target. The narrator emphasizes that the MG-42 wastes ammunition with its high rate of fire, that it's less accurate than American weapons, that its rapid fire makes it harder to control. The German gun is good, the narrator admits, but ours is better. It was obvious propaganda even at the time, and soldiers who had experienced MG-42 fire in actual combat were not fooled. But the film's very production reveals how seriously the army took the psychological threat the weapon posed. The reality, as captured in numerous after-action reports and soldier testimonies, was considerably less reassuring than the training film suggested. A junior officer who fought in Sicily provided this assessment in an intelligence document from early 1944. It's true that the Germans have a good machine gun, but, like many other German weapons, it doesn't live up to all the latrine rumours you hear. It doesn't walk on its hind legs or jump through hoops or anything like that. It's just a good, fast gun. I feel that the sooner our men understand how the Germans use it tactically, the more success we'll have in combating it. His words suggest both respect for the weapon and frustration with the mythology that had grown up around it. Other soldiers provided more specific tactical observations. One noted that German machine gun fire is usually so low, often about 1.5 feet above the ground, that we call it grass cutting. The Germans know that US soldiers don't allow their wounded to lie around any longer than is necessary, and that a man who has a leg wound of some kind will probably need a helping hand to get him to safety. It's fairly obvious that the Germans know the value of immobilizing as many men as possible at one time. This was sophisticated tactical thinking, made possible by the MG-42's capabilities. By deliberately aiming low, German gunners could wound rather than kill, creating casualties that required multiple soldiers to evacuate, thus removing more men from the immediate battle than killing them outright would accomplish. It was coldly efficient, and it worked because the weapon could maintain such devastating volumes of fire that wounded men couldn't be safely recovered until the gun position was neutralized. Another American officer observed, "Although the German machine gun is first-rate as to firepower, its dispersion is poor." One of my friends had so much confidence in his ability to get away from it that on one occasion, even though he had already received a number of shoulder wounds, he made a successful dash for safety and then turned and got the machine gunner with rifle fire 3 shots in the stomach. This observation captures an important reality. The MG-42, for all its fearsome capabilities, was not invincible. Its high rate of fire meant it burned through ammunition rapidly, creating resupply problems. Its accuracy from a bipod-mounted position was limited. A cool-headed soldier who understood the weapon's characteristics and limitations could exploit those weaknesses. But acquiring that cool-headed understanding required surviving multiple encounters with the weapon, and many soldiers did not. The casualty statistics tell their own story. While exact figures attributing deaths to specific weapons are impossible to determine, analysis of wound patterns and battlefield reports suggests that German machine guns, particularly the MG-42, accounted for a disproportionate number of Allied casualties in the European theatre. One study of American casualties in Normandy found that roughly 70% of wounds were caused by artillery and mortar fragments, with the remaining 30% roughly evenly divided between small arms fire and other causes. But within that small arms category, wounds inflicted during assaults on defended positions, precisely the situations where German machine guns were most effectively employed, predominated. The MG-42 shaped how infantry combat was conducted in ways both obvious and subtle. The weapon's influence extended beyond immediate tactical considerations to fundamental questions of industrial production and engineering philosophy. By late 1943, American ordnance authorities were forced to confront an uncomfortable reality. The Germans had achieved something American industry had not seriously attempted. They had created a weapon that was simultaneously cheaper, faster to produce, more reliable under adverse conditions, and more effective in its primary role than anything the United States military possessed. This realization prompted serious discussions about whether American industry should attempt to replicate German manufacturing techniques. The result of those discussions was the T-24 machine gun project, an attempt to reverse engineer the MG-42 for American use that would become one of the most embarrassing failures in U.S. ordnance history. The project began in earnest in early 1943, following the publication of the first comprehensive American assessment of the MG-42. The report, based on extensive testing at Aberdeen Proving Ground and other facilities, noted that the quick barrel changing and belt feed systems were considered some of its best design features. The U.S. Army wanted to manufacture this general-purpose machine gun because it was lighter and simpler to make than other American light and medium machine guns. The decision was made to convert several captured MG-42s to fire .30-06 Springfield ammunition, the standard American cartridge, and use those conversions as the basis for American production. The contract went to Saginaw Steering Gear, a division of General Motors with extensive experience in precision manufacturing and wartime production conversion. If anyone could successfully reverse engineer a German weapon, it should have been Saginaw. They had the manufacturing expertise, the engineering talent, the resources, and captured examples of the weapon to study. The engineers at Saginaw began their work with confidence. They stripped down captured MG-42s, measured every component, analyzed the metallurgy, studied the operating mechanism, and set about creating American versions chambered for .30-06 ammunition. The design was modified as minimally as possible to maintain the weapon's essential characteristics while adapting it to American ammunition. Two prototype weapons were produced, designated T-24. They looked nearly identical to the German original, featuring the same stamped steel construction, the same roller locking mechanism, and the same quick-change barrel system. On paper, the T-24 should have worked. In practice, it failed spectacularly. Testing began in January of 1944 at Aberdeen Proving Ground in Maryland. The first prototype was loaded with a belt of .30-06 ammunition, and an ordnance specialist pulled the trigger. The gun fired exactly one shot. Then it jammed, failing to eject the spent cartridge case. The testers cleared the malfunction and tried again. One shot, jam. The weapon simply refused to function. The second prototype performed slightly better. It at least managed to fire multiple rounds before experiencing failures, but it was plagued by constant ejection problems and feeding difficulties. During the testing period from January to February 1944, the weapon suffered 51 malfunctions after firing only 1,583 rounds. The average cyclic rate of fire, when the gun actually worked, was 614 rounds per minute, barely faster than existing American machine guns, and nowhere close to the MG-42's 1,200 rounds per minute. By March 1944, the U.S. military reached its conclusion. The official report stated that functioning of the T-24 machine gun prototype was unsatisfactory and recommended that further development was required before this weapon be subjected to the lengthy and severe standard but light machine gun test. This was military bureaucratic language for "it doesn't work, and we're abandoning the project." The reason for the failure was eventually determined. The .30-06 Springfield cartridge was too long for the weapon's roller locking mechanism to reliably handle. The MG-42 had been designed around the 7.92 by 57 mm Mauser cartridge, which had different dimensional characteristics and operating pressures. Simply chambering the weapon for a different cartridge wasn't enough. The entire DOT operating system would need to be redesigned from the ground up. And if you were going to redesign the operating system, you might as well design an entirely new weapon rather than trying to copy the German one. The T-24's failure revealed something profound about the MG-42's design sophistication. What had looked crude and simple was actually a carefully balanced system where every component worked in precise relationship to every other component. The stamped metal construction, the roller locking mechanism, the recoil operation, the feed system, the barrel design, all of these elements had been optimized to work together with the specific 7.92 mm Mauser cartridge under specific conditions. Change one variable, and the entire system stopped functioning reliably. The Germans hadn't simply stamped out metal parts and bolted them together. They had conducted sophisticated engineering analysis, materials science research, and extensive testing to create a weapon that only appeared simple. The apparent crudeness was actually elegant simplification, the removal of everything unnecessary to achieve maximum effect with minimum resources. This realization forced American ordnance authorities to reconsider their fundamental assumptions about weapons design. A report from this period recommended that a new type machine gun be designed, based on the German machine gun if necessary, in which stampings will take the place of expensive machine parts, and in which headspace adjustment will not be necessary. A gun patterned after the German machine gun is adaptable to mass production methods of manufacture and can be turned out at a fraction of the cost and in greater quantity. The recommendation also suggested consideration should be given to the design of a gun with an adjustable rate of fire, which can be varied between that of the Browning and of the German machine gun. These recommendations would eventually influence post-war American machine gun development, but they came too late to affect World War II production. Meanwhile, on battlefields across Europe, American soldiers continued to face the MG-42 under increasingly desperate circumstances. The weapon reached its peak deployment in 1944, when Germany was defending on all fronts and needed maximum defensive firepower from minimum personnel. That year, German industry produced 211,806 MG-42s, the highest annual production of the war. These weapons flooded into German units across the Eastern Front, in Italy, in France, defending every position that the Wehrmacht sought to hold. The MG-42 became ubiquitous, the signature sound of German defensive tactics from the ruins of Cassino to the hedgerows of Normandy to the frozen forests of the Ardennes. The weapon's effectiveness in defensive roles was particularly notable at Monte Cassino in Italy, where German paratroopers held Allied forces for nearly 4 months from January to May of 1944. The Fallschirmjäger, German airborne troops, were elite units trained in the aggressive use of automatic weapons. They transformed the ruins of the monastery and surrounding hills into a fortress, citing their MG-42s to create interlocking fields of fire that covered every approach. Allied forces attacking up the steep slopes toward German positions had to cross open ground under sustained machine gun fire from multiple positions simultaneously. The casualty rates were appalling. Polish troops of the Second Corps, who finally captured the monastery in May, left 1,293 dead in the rubble, with another 4,000 wounded. While artillery and mortar fire inflicted many of these casualties, the testimony of survivors consistently emphasized the devastating effect of German machine guns in preventing movement across exposed terrain. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The most famous or infamous employment of the MG-42 came on June 6, 1944, during the Allied invasion of Normandy. On Omaha Beach, German defensive positions overlooked the landing zones from elevated positions on the bluffs. These positions, designated Widerstandsnests or resistance nests, were concrete bunkers and fortified positions equipped with multiple weapons, including artillery, mortars, and machine guns. One of these positions, Widerstandsnest 62, was manned by Obergefreiter Heinrich Sevelow, a German soldier who would later become known, somewhat sensationally, as the Beast of Omaha. Sevelow's post-war memoir claims he personally fired 13,500 rounds through his MG-42 during the invasion, inflicting over 2,000 casualties on American forces storming the beach below his position. These numbers are almost certainly exaggerated. Total casualties on Omaha Beach from all sources were roughly 3,700. But the claim is revealing for what it says about the MG-42's reputation. Even if Sevelow's personal tally is inflated by a factor of 10, the fact that anyone would believe a single machine gunner could fire that many rounds and inflict that many casualties speaks to the weapon's established reputation for devastating effectiveness. What is verifiable is that German machine gun positions on the bluffs above Omaha Beach inflicted severe casualties on American forces during the critical early hours of the invasion. First-wave assault troops suffered casualty rates approaching 90% in some sectors. While many of these casualties came from artillery and mortar fire, the interlocking machine gun fire from positions like Widerstandsnest 62 made it nearly impossible for troops to advance across the beach or find cover. Contemporary accounts from American soldiers who survived Omaha Beach consistently emphasize the terror of being pinned down on open sand while German machine guns raked the beach. One survivor recalled, "The sound was everywhere. You couldn't tell where it was coming from, the bluffs, the bunkers. It seemed to come from every direction at once. That tearing sound, like the whole world was being ripped apart. Men were getting cut down before they even got off the landing craft ramps." Another described lying flat in the sand, trying to use bodies of dead soldiers for cover, while tracers from German machine guns formed an almost solid wall of fire above the beach. You could see the tracers. Every fifth round was a tracer, and there were so many of them it looked like a solid sheet of light. If you raised your head even 6 inches, you knew you were dead. The casualty toll on Omaha Beach, while caused by multiple weapon systems working in coordination, represented the MG-42's effectiveness in its ideal tactical employment. German doctrine called for machine guns to be sited in mutually supporting positions with overlapping fields of fire, positioned to cover obstacles and channeling enemy movement into kill zones, protected by other defensive positions to prevent flanking attacks. Omaha Beach exemplified this doctrine perfectly. The German defenders had months to prepare their positions, to calculate precise firing angles, to stockpile ammunition, to rehearse their defensive plans. When American troops landed, they walked into a killing ground that had been carefully prepared with German engineering precision. The MG-42s were only one component of this defensive system, but they were the component that created the continuous suppressive fire that prevented American forces from moving, from finding cover, from organizing effective assaults on the German positions. The beach was eventually taken, of course. American forces, despite devastating casualties, maintained pressure on German positions throughout the day. Naval gunfire and aerial bombardment gradually degraded German defensive positions. Small groups of infantry found ways to infiltrate the bluffs, attacking German positions from the flanks and rear. By nightfall of June 6th, American forces had established a precarious toehold on Omaha Beach, though at terrible cost. The lesson, if there was one, was not that the MG-42 could be easily countered. It was that American forces could absorb casualties that would have broken other armies and continue attacking until German positions were overrun through sheer determination and material superiority. This pattern repeated itself across the European theatre throughout 1944 and into 1945. German forces, increasingly outnumbered and outgunned, relied on the MG-42's firepower to compensate for their numerical inferiority. A well-sited machine gun position, properly supplied with ammunition and supported by other weapons, could hold up advancing Allied forces many times its size, at least temporarily. The Allied response was typically to call in artillery fire or airstrikes to suppress or destroy the German position, then advance under the cover of overwhelming firepower. This was effective but costly in time, in ammunition expenditure, and frequently in casualties. The alternative infantry assaults without preparatory fires was possible, but resulted in prohibitive losses. American soldiers developed various tactical responses to the MG-42 threat. Small unit leaders learned to use terrain more effectively, to move from cover to cover rather than attempting to cross open ground, to coordinate suppressive fire from their own weapons while maneuvering elements flanked German positions. The Browning automatic rifle, while slower firing than the MG-42, was effective for suppressing individual machine gun positions long enough for riflemen to advance. Mortar, Teams learned to respond quickly when German machine guns opened fire, dropping high-explosive rounds on suspected positions. Tank support, when available, provided both mobile cover for infantry and direct fire capability against fortified positions. None of these solutions eliminated the threat, they merely made it manageable, gave infantry squads a chance to close with and destroy German positions without being annihilated in the attempt. But the psychological toll remained significant throughout the war. Veterans of the European theatre carried memories of that distinctive sound for the rest of their lives. In the decades after the war, some would experience involuntary stress responses when they heard certain noises: a drill press, a sewing machine, fabric being torn, any sound that approximated that tearing roar. This was not weakness or cowardice. It was the entirely rational response of a nervous system that had been conditioned, through repeated exposure under life-threatening circumstances, to associate that specific sound with imminent death. Modern understanding of post-traumatic stress would recognize these responses as normal reactions to sustained combat exposure. In the 1940s and 50s, veterans simply lived with them, often in silence, understanding that no one who hadn't experienced that sound in combat could truly comprehend its psychological impact. The German military's own assessment of the MG-42 was consistently positive throughout the war. Captured training manuals and after-action reports describe it as reliable, effective, and well-suited to German tactical doctrine. German soldiers appreciated its firepower, its reliability under adverse conditions, and its relatively light weight compared to other medium machine guns. At roughly 25 pounds, it was substantially lighter than water-cooled heavy machine guns while providing comparable firepower. The quick-change barrel system was particularly valued. German machine gunners could maintain sustained fire far longer than their Allied counterparts, without being forced to cease fire for barrel changes. The weapon's main drawback, acknowledged in German tactical doctrine, was its prodigious ammunition consumption. At 1,200 rounds per minute, even a short burst consumed more ammunition than Allied machine guns would fire in sustained bursts. This required German infantry squads to dedicate significant personnel to ammunition. Carrying typically 3 riflemen in a 6-man machine gun crew carried nothing but ammunition, spare barrels, and tools. This ammunition consumption became increasingly problematic as German logistics deteriorated in the final year of the war. By late 1944, many German units were experiencing severe ammunition shortages. Machine gunners were instructed to fire shorter bursts, to carefully select targets, to conserve ammunition for critical moments. This reduced the MG-42's effectiveness somewhat, but even with restricted ammunition, it remained a formidable weapon. A short burst of 20 or 30 rounds from an MG-42, representing only 1 or 2 seconds of fire, still put more lead downrange than comparable bursts from Allied machine guns. German defenders in the Ardennes offensive of December 1944, despite severe ammunition constraints, still used their MG-42s effectively enough to inflict heavy casualties on American forces during the initial German breakthrough. The weapon's influence on post-war military thinking was profound and lasting. When World War II ended in May 1945, Allied forces captured hundreds of thousands of MG-42s. Many were simply destroyed as part of general disarmament, but many others were retained, studied, and eventually put into service by the armies of various nations. France adopted captured MG-42s for use by French forces, rechambering some for French 8mm Lebel ammunition. Yugoslavia not only used captured weapons, but reverse-engineered the design and began domestic production of a near-identical copy designated the M53. Various African and Asian nations that received military aid from either Western or Eastern Bloc countries during the Cold War ended up with MG-42s or derivatives, and some of these weapons remained in service well into the 21st century. But the most remarkable legacy of the MG-42 came from Germany itself. When West Germany rearmed in the 1950s and joined NATO, the new Bundeswehr needed modern military equipment, including machine guns. There was extensive debate about whether to adopt an American or British design, to develop something entirely new, or to resurrect German weapons from before the Nazi era. In the end, the Bundeswehr chose to put the MG-42 back into production. There was one significant problem. The original engineering drawings had been destroyed at the war's end as part of Allied disarmament policies. The Germans solved this by obtaining an MG-42 from a museum collection in the United States, transporting it to Germany, completely disassembling it, measuring every component with precision instruments, and creating entirely new engineering drawings from the physical weapon. The new version, modified to fire the 7.62mm NATO cartridge rather than the original 7.92mm Mauser round, was designated the MG-1. It was virtually identical to the wartime MG-42 in all essential characteristics: same operating mechanism, same rate of fire, same quick-change barrel system, same basic design philosophy. Later versions incorporated minor improvements and were redesignated the MG-1A3 and eventually the MG-3. The German military used versions of the MG-42 design continuously from the 1950s through the present day, over 70 years of TSAT service, making it one of the longest-serving military firearms designs in history. Other nations adopted the design as well. Austria produced the MG-74, Italy manufactured the MG-42/59, and various other countries either purchased German-made weapons or produced local variants under license. The influence extended beyond direct copies to the broader category of general-purpose machine guns. The MG-42 had demonstrated that a single weapon could effectively fulfill multiple roles: light machine gun, medium machine gun, vehicle-mounted weapon, even limited anti-aircraft capability if properly designed. This general-purpose concept revolutionized post-war machine gun development. The American M60 machine gun, introduced in the late 1950s as a replacement for the various Browning designs, incorporated design elements influenced by study of the MG-42, particularly the quick-change barrel system and the general-purpose concept. The Belgian FN Mag, perhaps the most successful general-purpose machine gun ever designed, was directly influenced by the MG-42's design philosophy and went on to be adopted by over 80 countries, including the United States, which designated it the M240. Today, American forces in combat around the world carry M240s that trace their conceptual lineage directly back to that weapon American soldiers once mocked for its stamped steel construction. The story of the MG-42 and American soldiers' reactions to it is ultimately a story about the danger of assumptions, about the gap between appearance and performance, about how preconceptions can blind us to reality until that reality becomes undeniable through bitter experience. When American ordnance officers first examined captured MG-42s in the autumn of 1942, they saw stamped metal and loose tolerances and concluded they were looking at evidence of German desperation and a declining quality. They were wrong. They were looking at sophisticated engineering that had achieved goals. American industry hadn't attempted creating a weapon that was simultaneously cheaper, faster to manufacture, more reliable, and more effective than supposedly superior traditionally manufactured designs. The Americans couldn't copy it successfully because it was far more sophisticated than it appeared, because the apparent simplicity was actually elegant complexity, because you can't reverse engineer intuitive manufacturing know-how by simply measuring dimensions. American soldiers in the field learned these lessons more directly and at higher cost. The man who laughed at stamped steel construction was, within weeks, diving for cover when that same stamped steel weapon opened fire on his position. The replacement soldier, who froze in terror at the MG-42's distinctive roar if he survived, eventually learned to function despite that fear, learned to use terrain and tactics to minimize exposure, learned that the weapon, for all its fearsome capabilities, could be defeated by infantry willing to accept casualties and maintain pressure on German positions. This knowledge was purchased with blood and measured in casualty statistics, and carried in the memories of veterans for the rest of their lives. The transformation of American attitudes toward the MG-42, from mockery to terror to grudging respect to attempted replication to lasting influence, represents a microcosm of broader American experiences in World War II. The United States entered the war confident in its industrial superiority, convinced that American manufacturing know-how and engineering excellence would overwhelm Axis forces through sheer material superiority. This confidence was not entirely misplaced. American industrial production did prove decisive in the war's outcome, but the path to victory required learning uncomfortable lessons about enemy capabilities, about the relationship between resources and innovation, about how desperation and material constraints could sometimes drive more creative solutions than abundance and established manufacturing traditions. The German military lost World War II despite possessing weapons like the MG-42, not because these weapons were ineffective, but because individual weapon superiority cannot overcome comprehensive strategic disadvantages. Germany was outnumbered, outproduced, fighting on multiple fronts against enemies with vastly greater resources. No amount of tactical innovation or weapons engineering excellence could compensate for fundamental strategic impossibilities. But within that broader context of inevitable defeat, the MG-42 represented German military engineering at perhaps its most effective, a weapon that achieved maximum effect with constrained resources, multiplied the combat power of infantry units, and influenced how battles were fought across every theatre of the European war. For American soldiers who faced the MG-42 in combat, these strategic considerations were abstractions. What mattered was the immediate tactical reality. Somewhere ahead, concealed in a fortified position or a hastily dug foxhole or the rubble of a destroyed building, a German soldier sat behind an MG-42 with belts of ammunition and spare barrels and orders to hold his position. Your job was to cross the open ground between your position and his, to close with and destroy that position, to accomplish the mission despite knowing that the weapon pointed in your direction could fire 20 rounds per second, could cut you literally in half if the gunner drew a bead on you, could maintain that devastating rate of fire for as long as ammunition held out. Some soldiers found the courage to move despite that knowledge. Some froze, some were killed, some survived, but none of them forgot the sound, that distinctive tearing roar, that buzzsaw scream that announced you were in, the presence of one of the most effective infantry weapons ever designed. Private First Class Leonard Liniewski, an army truck driver, was driving through a recently secured area in Belgium in late 1944 when he spotted an abandoned MG-42 in a field beside the road. Liniewski, being an enterprising soldier far from the direct oversight of officers, stopped his truck and retrieved the weapon. He intended to keep it as a war trophy, a souvenir to take home when the war ended. There was one problem. As a support soldier, Liniewski had no idea how to disassemble the gun for transport or storage. So he held onto the weapon, carrying it with him as his unit moved through Belgium and into Germany, until he eventually found a camp holding German prisoners of war. He convinced captured German soldiers, men who had used the weapon in combat, to show him how to properly break it down. That captured MG-42, which Liniewski did eventually take home, is now part of the collection at the National World War II Museum in New Orleans, where visitors can examine it and reflect on its history. Think about what Liniewski's story represents. An American soldier wanted this weapon, not a Luger pistol, not a Nazi flag, not a helmet or bayonet or any of the other common war trophies, but specifically an MG-42. He wanted it badly enough to keep it with him for weeks or months, despite the logistical inconvenience of carrying a 25-pound machine gun that wasn't part of his regular equipment. He wanted it badly enough to approach enemy prisoners of war and ask for their assistance. This wasn't the behavior of a man who viewed the weapon as crude German scrap metal. This was the behavior of a man who recognized, as thousands of other American soldiers had come to recognize through direct experience, that he was in possession of something remarkable, something that represented the pinnacle of a particular type of military engineering, something worth keeping despite all rational arguments against doing so. Liniewski's impulse to acquire the weapon as a trophy was shared by thousands of other American soldiers. After-action reports from across the European theatre mention soldiers attempting to retain captured MG-42s, trying to get them back to rear areas, asking superiors if they could keep them. This stood in stark contrast to soldiers' attitudes toward other captured German weapons. Carabiner 98 rifles were curiosities, examined and then discarded or turned into intelligence officers. Luger pistols were prized for their cachet as trophies, but not particularly valued as functional weapons. But MG-42s? Soldiers wanted those. They wanted to test them, to fire them, to understand how they worked, to possess them as tangible evidence that they had faced and survived the most fearsome infantry weapon on the battlefield. This transformation from mockery to acquisition occurred over the span of roughly 30 months, from summer 1942, when American forces first encountered the weapon in Tunisia, to spring 1945, when the war in Europe ended. 30 months during which hundreds of thousands of American soldiers rotated through combat zones, during which the MG-42 fired billions of rounds at Allied forces, during which its distinctive sound became as much a part of the European battlefield's audio landscape as artillery fire or aircraft engines. 30 months during which American assumptions about German engineering capabilities underwent fundamental revision, forced by reality, paid for in casualties, proven in the failure of the T-24 project and the success of German defensive tactics built around the weapon. The final irony is that American forces defeated Germany despite the MG-42, not by matching its capabilities or copying its design, but by accepting that some enemy weapons were superior in specific categories and compensating through superiority in other areas. American forces had better logistics, better artillery support, better air power, better strategic mobility, and ultimately greater numbers. They could call in fire support that German forces couldn't match. They could replace casualties at rates German units couldn't sustain. They could maintain offensive pressure continuously while German forces, even with superior weapons, had to husband their limited resources and eventually retreat or be destroyed. The MG-42 was a magnificent weapon, perhaps the best machine gun of World War II, but magnificence alone does not win wars when your nation is outmatched strategically, industrially, and numerically. For the individual soldier facing that weapon in combat, strategic considerations provided no comfort. You still had to cross the open ground. You still had to assault the position. You still had to hear that sound and move toward it, despite every survival instinct screaming at you to stay down, stay hidden, stay safe. The soldiers who did this, who functioned effectively despite fear, who completed missions despite casualties, who maintained cohesion and discipline under the stress of sustained combat, deserve recognition not just for their courage, but for their adaptability. They learned, faster than their doctrine and training had prepared them to learn, how to fight against an enemy who held tactical advantages in specific areas. They learned to respect enemy capabilities without being paralyzed by that respect. They learned that superior weapons could be overcome through superior tactics, through accepting necessary risks, through maintaining pressure even when casualties mounted. Thank you for reading. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.